Good morning students. Today we are going to discuss about Opamp parameters and the concept of feedback. There are 9 Opamp parameters. They are input bias current, input offset current, input offset voltage, output offset voltage, CMRR, slew rate, open loop gain, input impedance and bandwidth. So first we shall see what is input bias current. Input bias current is the average of the currents that enter into the two input terminals of the op-amp with the output at 0 volts. We know the two input terminals are inverting terminal and non-inverting terminal. So it is the average of the currents that enter into the two input terminals when the output is 0. Next, input offset current. It is the difference between the two input currents of the op-amp when the output is 0 volts. So input bias current is the average of the currents, whereas input offset current is the difference between the two input currents. Next, input offset voltage. It is the voltage applied between the two input terminals of the op-amp to nullify the output. The voltage applied between the inverting terminal and the non-inverting terminal to make the output 0. Next, output offset voltage. It is the 0 output voltage without any input voltage applied. Okay, it is the 0 output voltage without any input voltage. Next, common mode rejection ratio. It is the ability of the differential amplifier to reject the common mode signal such as noise. That is the capacity of the op-amp to reject the unwanted signals. It is expressed in decibels and it is denoted by rho. So larger the CMRR, better is the op-amp to eliminate the unwanted signals. It is defined as the ratio of differential mode gain AD to the common mode gain ACM. So AD is differential voltage gain and ACM is the common mode voltage gain. So CMRR is equal to differential voltage gain by common mode voltage gain, that is equal to AD by ACM. Next, slew rate. It is defined as the maximum rate of change of output voltage per unit time, and it is expressed in volts per microsecond. So for output voltage the unit is volt, for time it is microsecond. So it is the maximum rate of change of output voltage per unit time. It is expressed as dV0 by dVO by dt max. Next, open loop gain AOL. It is the gain of the op-amp without a positive or negative feedback. So the word open loop refers to the op-amp without a feedback. Next, input impedance. Impedance is nothing but resistance. According to Ohm's law, resistance is equal to voltage by current. So it is the ratio of input voltage to the input current, since it is the input impedance. Next is bandwidth. Bandwidth represents the width of frequencies or the band of frequencies that the amplifier is most effective in amplifying. So bandwidth is the band of frequencies where the amplifier can effectively amplify the input signals. Next, ideal op-amp characteristics. Infinite input impedance. Input impedance, the symbol is Zi. It is infinite, and 0 output impedance, that is Zo, is 0. Infinite voltage gain. Gain symbol is A. Since it is voltage gain, it is AV. AV is infinite. Next, infinite bandwidth. BW is infinite. Infinite common mode rejection ratio, that is CMRR, is infinite. Slew rate is infinite. 0 offset voltage. It is nothing but when the two inputs are equal, the output voltage is 0. And all the above characteristics do not change with temperature. These are the ideal op-amp characteristics. Now we can compare the ideal op-amp parameters with practical op-amp. So the parameters are, the first parameter, open loop gain, symbol A. Ideal op-amp it is infinite. For practical op-amp it is 2 into 10 to the power 5. Input impedance Zi. Ideal op-amp infinite. Practical op-amp 2 mega ohms. Next, output impedance, it is ZO. For ideal it is 0. For practical it is 75 ohms. Input offset voltage, symbol is VIO. For ideal it is 0. For practical it is 5 millivolts. Input bias current, symbol IB. For ideal it is 0. For practical 500 nanoamps. Bandwidth, symbol BW. For ideal it is infinite. For practical it is 1 megahertz. Common mode rejection ratio, symbol CMRR. Infinite for ideal and 90 decibel for practical op-amp. Slew rate, symbol SR. Infinite for ideal and 0.5 volt per microsecond for practical op-amp. Next, input offset drift current, it is 0 for ideal, 0.1 nanoamps per degree centigrade for practical op-amp. Input offset voltage drift, it is 0 for ideal and 7 microvolt per degree centigrade for practical op-amp. So these are the comparison of op-amp parameters of ideal and practical op-amp. Next, the concept of feedback. So feedback is a process in which a portion of the output signal is fed back to the input and it is recombined with the input. You can see in this diagram the portion of the output is fed back to the input and it is recombined with the input. And this path, that is the path over which the feedback is amplified, is called feedback loop or the feedback path. There are two types of feedback. They are positive feedback and negative feedback. In the amplifier without feedback, gain is represented by A, which is the ratio of output voltage to the input voltage. That is, A is equal to VO by VI. In an amplifier with the feedback, a fraction of the output signal or the output voltage VF is returned back to the input. Therefore, the feedback voltage VF is equal to beta VO, where beta is equal to VF by VO. This is called a feedback ratio or a feedback fraction. And this voltage is added for positive feedback and subtracted for negative feedback. Okay, so for positive feedback we are going to add VF with the signal voltage. So VI is equal to Vs plus Vf, that is equal to Vs plus beta VO. And this voltage is subtracted for the negative feedback, that is Vi is equal to Vs minus Vf, that is equal to Vs minus beta VO, where Vs is the signal voltage. Next comes positive feedback. So as the name implies, positive feedback is obtained by applying a small part of the output voltage back to the non-inverting terminal. So for the non-inverting terminal the symbol is plus. So a small fraction of the output voltage is fed back to the non-inverting input terminal through a feedback resistor RF. And in this feedback, the amplifier and the feedback network each introduces a phase shift of 180 degree, making a 360 degree resultant phase shift around the loop. Okay. So in the case of positive feedback, the amplifier and the feedback network each introduces a phase shift of 180 degree. So the total is 360 degree. Hence the output voltage is in phase with the input voltage. There is no change. Okay. The output signal is in phase with the input signal. So if the input voltage Vi is positive, the op-amp amplifies this positive signal and the output becomes more positive. And because of this feedback, what happens? Some of this output voltage is returned back to the input by the feedback network, making the input much more positive. So this happens and we will get a larger output and so on. Okay. So this is the process behind positive feedback. Now the expression for gain. As I said, the feedback voltage is added to the input signal. So the input voltage is given by Vi is equal to Vs plus beta Vo. Since A is equal to Vo by Vi, this implies Vo is equal to A into Vi. That's equal to A into, substitute this Vi, so we get Vs plus beta Vo. Therefore Vo is equal to AVS plus A beta Vo. You multiply each term inside the bracket with A. Therefore AVS is equal to Vo minus A beta Vo. Upon rearranging, you bring Vo towards one side. So we get AVS is equal to Vo minus A beta Vo. Now Vo is common in this, take it out. So Vo into 1 minus A beta. What is the formula for gain? Gain is equal to output voltage by input voltage. So here we have output voltage by signal voltage Vs, that is equal to A divided by 1 minus A beta. So in this equation, you keep Vo as it is, bring Vs to the denominator, that is by cross multiplication, bring Vs to the denominator and we get A divided by 1 minus A beta is equal to AF, where AF is the overall gain of the amplifier with feedback. Thus feedback is defined as the ratio of output voltage to the input signal voltage. Though the positive feedback increases the gain of the amplifier, it has disadvantages such as increasing distortion and instability. So it produces a lot of noise or unwanted signals and the output is unstable. So because of these advantages, positive feedback is not used in amplifiers. And if the feedback is sufficiently large, it leads to oscillations. Hence, positive feedback is used in oscillators and not in amplifiers. Next, negative feedback. As the name implies, negative feedback is obtained by applying a small portion of the output voltage back to the inverting input terminal. Okay, the output voltage, if you see this diagram, the output voltage is supplied to the inverting input terminal. The symbol for inverting input terminal is minus. So the output voltage is fed back to the inverting input terminal through the feedback resistor RF. Here the amplifier produces the phase shift of 180 degree, while the feedback network does not produce any phase shift. So the resultant feedback voltage is 180 degree out of phase with the input signal Vi. Whereas in the case of positive feedback, the amplifier and the feedback network each introduces a phase shift of 180 degree. So the resultant is 360 degree. Hence the input and output signal both are in phase. Whereas in the negative feedback, they are out of phase. Next is input voltage gain. It is given by Vi is equal to Vs minus beta Vo. Again, A is equal to VO by VI. Therefore, VO is equal to A into VI. Substitute for VI from this equation, and after substituting, multiply each term inside the bracket. So we get VO is equal to AVS minus A beta VO. Now group the VO terms. So AVS is equal to VO plus A beta VO. That's equal to taking VO outside, VO into 1 plus A beta. VO by Vs is equal to A by 1 plus A beta. This we get by cross multiplying the above equation. That's equal to AF, where AF is the overall gain of the op-amp with negative feedback. Though the gain of the negative feedback is less, there are many advantages such as stability in gain, reduction in distortion, reduction in noise, etc. Hence, negative feedback is used in amplifiers, not in oscillators. Now, advantages of feedback. Feedback networks are widely used in amplifier circuits, oscillators, process control systems, and many other electronic systems. The circuit characteristics such as system gain, frequency response, and bandwidth can be precisely controlled. That is, we can accurately control system gain, frequency response, and bandwidth. Next, circuit characteristics such as the system gain, frequency response, these can be made independent of the operating conditions like supply voltage or temperature variations. That is, even if there is voltage fluctuation or temperature variation, it will not affect the circuit characteristics. Next, signal distortion can be reduced to desired extent. That is, to a certain extent, to the required extent, we can reduce the unwanted signal. Okay, these are all about op-amp parameters and the concept of feedback. Hope you all understood. Thank you.